At this very moment, while you're hearing these words, a spacecraft built in the 1970s is racing through space at over 17 kilometers per second, nearly 24 billion kilometers separated from Earth. Its radio signal needs more than 22 hours to arrive. Its power supply is weakening. Its onboard systems predate the first personal computers, and yet the data it continues to send back is forcing scientists to reconsider models that stood unchallenged for decades. Voyager 1 was never intended for this. It was designed to conduct a planetary tour lasting 4 years. Instead, 46 years later, it has crossed the edge of the sun's domain, entered interstellar space, and returned measurements that do not fully align with theory. The boundary appeared in an unexpected location. The magnetic field failed to shift as predicted. Plasma temperatures were higher than anticipated. Density rose in ways that challenged long-held assumptions. The heliosphere, once imagined as a tidy, protective bubble, revealed itself to be dynamic, asymmetrical, and strangely porous. This is not merely a story about distance. It is the story of a frontier that refused to behave according to plan, and it begins long before Voyager left Earth. In the early 1970s, at NASA Jet Propulsion Laboratory, engineer Gary Flandreau noticed something remarkable. While calculating trajectories to the outer planets, Jupiter, Saturn, Uranus, and Neptune were aligning in a rare geometric configuration that occurs only once every 175 years. This alignment meant a spacecraft could use successive gravitational assists, gaining speed and redirecting its path, like a surfer riding a perfectly timed cosmic wave. Without this opportunity, reaching Neptune would have required far more energy and decades of additional travel. The original concept, known as the Grand Tour, envisioned 4 large spacecraft visiting all the outer planets in one continuous chain. It was ambitious and expensive. The United States Congress rejected it due to budget constraints. Instead, a scaled-down mission was approved. 2 smaller spacecraft focused primarily on Jupiter and Saturn. What was not emphasized publicly, but was understood within NASA, was that these spacecraft were engineered with the potential to travel far beyond if they survived. Voyager 2 launched first on August 20th, 1977, aboard a Titan III rocket from Cape Canaveral. 16 days later, Voyager 1 followed on September 5th. Though launched second, Voyager 1 took a faster, more direct path and would arrive at Jupiter first. The numbering reflected arrival order, not launch sequence. Each spacecraft weighed about 825 kilograms and carried 10 scientific instruments, cameras, spectrometers, magnetometers, plasma detectors, and charged particle sensors. But attached to each was something with no immediate scientific purpose: a gold-plated phonograph record. It contained 116 images of Earth greetings in 55 languages, 90 minutes of music, from Bach and Beethoven to Chuck Berry, the sound of wind and waves, a human heartbeat, and messages from global leaders. The selection was overseen by Carl Sagan, who later explained that the record was as much a message to ourselves as to any distant civilization, proof that we could think beyond our own lifetimes. But before that message could drift into the galaxy, there were planets to visit. When Voyager 1 reached Jupiter in March 1979, scientists expected refinement, not revolution. Instead, the spacecraft revealed active volcanoes erupting on Io, the first confirmed volcanic activity beyond Earth. Sulfur plumes soared hundreds of kilometers above the surface. What was assumed to be a frozen moon was in fact the most volcanically active body in the solar system, heated by tidal forces from Jupiter and neighboring moons. Europa, told a different story. Its smooth, fractured surface suggested a geologically young crust. Beneath the ice, scientists propose a global subsurface ocean, a possibility that transformed Europa into a prime candidate in the search for life. Jupiter itself astonished observers. The Great Red Spot churned in extraordinary detail, a storm large enough to engulf 3 Earths. Lightning flashed, auroras shimmered. Its magnetosphere proved vastly stronger than expected. At Saturn in November 1980, Voyager once again overturned assumptions. The rings, once thought simple, were revealed as thousands of intricate divisions with braided structures and mysterious spokes influenced by electromagnetic forces. Titan shocked scientists with its thick nitrogen atmosphere and complex organic chemistry. Voyager 2 later extended the mission to Uranus in 1986 and Neptune in 1989, completing what the Grand Tour had once imagined. Uranus rolled along its orbit tilted at 98 degrees, essentially rotating on its side. Its magnetic field was oddly offset and skewed, defying planetary models. Neptune delivered supersonic winds, approaching 2,000 kilometers per hour, the fastest in the solar system. Its great dark spots swirled in the frigid atmosphere, and Triton revealed active nitrogen geysers despite surface temperatures near minus 235 degrees Celsius. By the end of the planetary tour, one truth was undeniable: the outer solar system was far more dynamic and strange than textbooks had predicted. After Saturn, Voyager 1 continued outward toward what scientists once imagined as a clear boundary, the edge of the solar system. That boundary was expected to behave like a line. Instead, Voyager found a layered, shifting transition. First came the termination shock, where the solar wind slowed abruptly. Beyond that lay the heliosheath, turbulent and chaotic. Cosmic ray levels rose as Voyager approached the outer limit of solar influence. But when it crossed the heliopause, the magnetic field did not swing sharply as predicted. The direction remained surprisingly similar. Only plasma oscillation data revealed the truth. The density outside was about 40 times greater than the solar wind. Voyager had entered interstellar space, yet the crossing was gradual, a porous, asymmetrical membrane shaped by both solar and galactic forces. Once beyond the heliosphere, Voyager discovered something equally unexpected. Interstellar space was not as cold and empty as imagined. Temperatures ranged between 30,000 and 50,000 degrees Celsius. The density was extremely low, about 0.1 atoms per cubic centimeter, but the particles carried significant energy. Voyager travels within the local interstellar cloud, embedded inside the larger local bubble, a vast cavity of low-density gas spanning roughly 1,000 light-years. The heliopause proved flexible, compressible, and dynamic. Plasma density increased gradually rather than dropping cleanly. A faint, persistent, low-frequency oscillation, almost a background hum, suggested that interstellar space is not silent, but alive with subtle motion. The frontier was not a wall. It was an interface. Popular imagination once described interstellar space as a perfect vacuum. Voyager showed otherwise. At speeds over 17 kilometers per second, even sparse particles carry impact energy. Cosmic rays accelerated by distant supernovae penetrate electronics and alter memory bits. Beyond the heliopause, cosmic ray intensity increased sharply as solar shielding weakened. The heliosphere, once thought nearly sealed, is partially permeable. Interstellar particles leak inward. Solar particles escape outward. This has implications not just for robotic probes, but for any future human attempt to follow. In late 2023, Voyager 1 reminded us of its fragility. It began transmitting corrupted data. Engineers traced the problem to its flight data system, possibly damaged by a high-energy cosmic ray strike. Its onboard computer contains just 69 kilobytes of memory. Commands require 22 hours to arrive and 22 hours for a reply. Engineers divided and rewrote the spacecraft's code, redistributing it across functioning memory, effectively reconfiguring a 1970s computer nearly 24 billion kilometers away. Weeks later, readable telemetry resumed. Meanwhile, its radioisotope generators lose about 4 watts of power each year. Instruments are gradually shut down to conserve energy. The countdown is real. Voyager survives not because space is gentle, but because it was built with extraordinary resilience. Voyager 1 was meant for a 4-year mission during a once-in-175-year alignment. It was supposed to photograph Jupiter and Saturn, gather data, and fade into silence. Instead, nearly half a century later, it travels through interstellar space, still transmitting, still challenging assumptions. The outer planets were not quiet worlds, but volcanic, ocean-bearing, magnetically twisted systems. The boundary of the sun's influence was not a line, but a turbulent membrane. Interstellar space was hotter, denser, and more dynamic than expected. The impossible discovery was not one number. It was a pattern. The solar system is more active than we imagined. Its boundary more complex. Interstellar space more energetic. Voyager did not encounter a wall. It found a living interface between the sun and the galaxy, and it continues, moving through it. Every year, for what's vanish. More instruments fall silent. Yet until the final what fades, Voyager remains our most distant witness, a machine built before the internet, carrying human engineering into a medium we are only beginning to understand. If this is what we have learned from one spacecraft, imagine what future missions may reveal. The frontier is not empty. It is waiting. If you want to follow the real discoveries unfolding at the edge of the sun's influence, the boundaries that refuse to behave, the physics that surprises us, the data still arriving. After nearly 50 years, stay with us, because Voyager 1 has not reached the end. It may have shown us that the end does not exist at all. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.